because of the exam. So your next set of homework, 2-4, and I think it's just 2-4 because I don't think we're going to finish it all today. We should hopefully finish it all by Thursday. But so your next homework that popped up today is going to cover just 2-4. So yeah, we are getting pretty far behind where we should be to cover all of the material for this class that we need to cover. So we might, need to start picking up the pace a little bit, but that's also my fault. So this class covers a lot of material. And we don't really have a lot of time to cover everything in as much detail as we should. Anyway, apart from that, so let's start with 2-4, which is called relations. So in this section, we're going to look at more kind of general relationships between sets, and we're going to develop this idea called modular arithmetic, which I think is really fun, but I'm weird. So recall when we were talking about sets in 2, the Cartesian product of the two sets is the set of all ordered pairs where the first element comes from the first set and the second element comes from the second set. So to remind us, say we had these two sets, 1, 4 and 1, 2, and 3. Let me reshare my screen really quick, just in case. If I wanted to write out the Cartesian product for these two sets, we'd have 1, 1, 1, 2, 1, 3. So essentially this first element with every single element of B. And then we jump to using 4 with every element of B. So 4, 1, 4, 2, 4, 3. So a reminder on that kind of Cartesian product idea. So essentially what we're going to do is we're going to have something called a relation. So a relation R on a set S. The lag is real. At least it is on my screen. Come on, catch up with me. This is another reason why we're so behind where we should be. Is everybody else's screen frozen? There it goes. So a relation R on a set S is a subset of essentially the set Cartesian producted with itself. Now that might sound super weird, but let's look at this example kind of right here. So essentially what we're doing is we're taking a set and we have some sort of relationship that's relating the elements in the set to itself, if you will. We don't necessarily have to use all of those values, but we can. So say we have this set S, which is 1, 2, and 5, then we could define the following relations. We could have a relation on the entire Cartesian product. So that would essentially look like if we do this Cartesian product with itself. So essentially we have the first element being 1, and then we put 1 with 1, 2, and 5. So we'd have 1, 1, 1, 2, and 1, 5. And then we'd move on to using 2 as our first element. So 2, 1, 2, 2, and 2, 5. And then 5, 1, 5, 2, 5, 5. So we're essentially taking that set and making the other set that same set, if you will. So we're kind of Cartesian. Yeah.
When we were doing unions and things like that before, if a thing was, if one of the symbols was the elements was repeated, that we just put one of them. So how come it's different for this part?
Because they're ordered pairs. So like this 1, 1 is one element. And this pair 1, 2 is one element. Now 2, 1 would be considered a completely different element because the order here actually matters. So like 2, 1 versus 1, 2, that's not the same thing. So it's not like we're repeating that. It's a different order, so it's a completely different element. But these pairs.
So it's because they're in the same. They're together with the comma. Is
yeah, essentially, okay. Since we're kind of grouping them in these parentheses, it's kind of making it, it's almost like a coordinate point. Like if you think about plotting points on the X and Y axis, you know, if you have 1, 2, that's not the same thing as 2, 1. That's kind of what we're doing here. You can almost think of these as acting as points where they're kind of grouped together to be one thing. So that's why it's slightly different than it was before, where we're not actually repeating them because they're different things, but I can kind of see why you might think that. But that's kind of what's happening here.
Okay, thank you.
Yep. Cleared up a little bit. So we could essentially just Cartesian product this thing with itself and essentially get this huge giant set. So that would be considered a relation, because to be a relation, you literally just have to be some subset of this thing. So the thing itself is a subset. So we could just take a relation to be that entire Cartesian product. Or we could also take it to be something that's not that whole thing. So say I just took 1, 2, and 1, 5. So, you know, those are two elements from this Cartesian product. So if I want to take a subset, I can essentially just pick out as many elements as I want. So maybe I just pick out these two. This would also be considered a relation because it is a subset of that Cartesian product. This is lagging a lot. At least on my screen. I don't know if your screen matches my screen, but my screens are lagging a lot. There we go. So essentially, relation, we have this kind of list of points, if you will, and we just have to take a subset of them. We can take all of them, we can take just a few of them, we can take none of them. That would have been more dramatic if it wrote it while I wrote it. There we go. So we could also take none of these. I'm going to kind of start referring to them as points because I just think that's the easiest way to refer to them. I could take none of them. So technically, I could also have a relation just be the empty set, because to be a relation, I literally just have to take some subset of this Cartesian product. Hopefully that makes sense. Now, sometimes in a relation, we actually have kind of a rule going on, which we'll see in a second. Sometimes it's just that we're saying that these things are related and we don't necessarily know how they're related. But sometimes we will know how they're related. We'll see an example of that in a second. So some notation, once it scrolls down, let me try unsharing and resharing and see if that helps a little bit. Because this is obnoxious. There we go. So some notation. So say we have some point, if you will, that's in the relation. Then, once again, here we go. So say we have this point that's in the relation that we're talking about. We would also write that as essentially A is related to B, but it's written like, oh, come on. There we go. So say that two things are related. We kind of say A, R, B. A is related to B. And say there was a certain point, if you will. Again, they're not really points, but I think it's the easiest way to refer to them. If that's not in the relation, then we would just say that A is not related to B. So just slash through the R. So we're going to kind of have this R notation to say whether or not two things are related to each other in the relation. Or shall I say that they are in the relation or not? Because if they're in the relation, then they're related to each other. If they're not in the relation, then they're not related to each other. So maybe I should try to zoom out a little bit so that, because this next thing refers to the thing above it. That's good enough. So this next example, it's going to pull, it's talking about the relations, you know, above. So number 1 in this one is related to the S cross S, and the second one is just related to the 1, 2, and 1, 5, and then the third one is related to the empty set one. So to refer back to that later, just so that we can remember what we're talking about, I'm just going to kind of put the relations next to them in case you're looking back at this later and forget that it's related to the thing above it. Anyway, So say we wanted to get used to using this notation. So in this S cross S option, which is essentially everything I could have, so essentially absolutely any element in that set S is going to be related to something else, because that was like, that first S cross S was all of our options. We set everything as a relation to every other thing. So essentially any element that would be in S is going to be related to Y in some way in this kind of entirety set, if you will. I'm saying my words are not good. Since the S cross S is the largest relation we can have in this case, everything's related to everything else, is what I'm trying to say. So we would say that X is related to Y for essentially any X or Y. That's what I'm trying to say. In the second one, we have a much smaller set because we only have 1 is related to 2 and 1 is related to 5. So we could say 1 is related to 2, and we could say 1 is related to 5 once it catches up to me. Oh my God, there we go. So we could say 1 is related to 2 and 1 is related to 5. But since, 5 comma 2 is not in that relation, it's not in, this set that we're talking about, since that point, if you will, isn't in that set, then 5 is not related to 2. And there's a lot of other things that aren't related as well, but that's one of the options. 5 comma 2 is not in that relation, so we would say 5 is not related to 2. Now, when we talk about the empty set relation, well, there's nothing in there. That's just empty. It's nothing. So essentially, for any element you could pick from the original set S, nothing is going to be related at all because we have that the relation is empty. So we'd have for any X and Y, they're not related to each other. So essentially, once we define these relations, if the, kind of point is in there, if you will, if it's in the set that we're considering to be the relation, we can say that the two elements are related to each other. If that kind of point is not in the set, then we say that they're not related to each other. So as I kind of said before, sometimes we have an actual rule that we want to follow, and sometimes we just don't know what it is. We're just told that these things are related to each other. But say we have this set S is 1, 4, and 7, and we want to define this relation to be essentially defined by a greater than symbol. So essentially we want to look at these numbers and order them based off of, not order them, I should not say order. We want to say they're related if one of the numbers is larger than the other. So essentially looking at 1, 4, and 7, before I write out the actual relation, we have 4 is greater than 1, we have 7 is greater than 1, and we have 7 is greater than 4. And those are the only things I can say. There's nothing else, no other way I can use these numbers in a way that actually makes a true statement. 4 is not greater than 7, 1's not greater than 4. So these are the only 3 true things that come from kind of defining this relation of greater than. So if I actually wanted to write out kind of the relation as a set, since 4 is greater than 1, 4 is related to 1, 7 is related to 1, and 7 is related to 4. I'm going to do a side note over here. It's really important to note that the order really does matter on these points, if you will. Again, they're not really points, but I think that just makes us think of the notation enough. Because especially in this case, if I were to say 4 is related to 1, well, that means 4 is greater than 1. But if I wanted to say 1 is related to 4, I'd be saying 1 is greater than 4, which is not true once it catches up to me. So you do want to be very careful about your order. The order definitely matters with these relations. If you're given the relation, do not change the order. If you have to find the relation. Be very careful of your notation and your order, because that'll definitely matter. Questions, concerns so far? Okay, I'll leave this up for like 5 more seconds before we move on to the next page in case people need to get caught up a little bit. And just one more time. So in this example 4, we're kind of given what the relationship actually means, because we're given the fact that the relation is based off of this greater than idea. A lot of times we're not going to know the actual relationship between the two numbers. We're just going to be told that they're related, and we're just going to have to trust to believe that they're related in some way. So moving on. Oh boy. There we go. So our relations functions. So recall that to be a function, each input must have one and only one output. In a relation, you can have an element that's related to a lot of other elements. So say we were looking at the original one. Nope, even just, here, let me just scroll back up really quick. Even in the one we just did, 7 was related to 1 and 4, once this catches up to me. So we essentially had this one input, if you will, that was related to 2 different things. So relations are definitely not necessarily a function. Essentially what we want to think of relations as is just kind of a comparison within a set, is we're taking these elements of a set and comparing them to the other elements. And again, sometimes we're going to know how we're comparing them and sometimes we're not. So one step further from just a general relation is that we have this idea of something called an equivalence relation. So a relation on a set S is going to be called an equivalence relation. Equivalence relation. If it satisfies the following 3 properties. It's got to be called something called reflexive, so reflexivity, which means for any element in your set, A is going to be related to itself. Now, most of the times here, nope, that's not even true, so I'm not going to say it. Never mind. So you just have to have that A is related to itself. For any elements in your set A and B, I should say, I'm going to say it like this instead of how I wrote it in my notes. If A is related to B, then B is also related to A. So essentially, if you have one of the things is related to another, then you kind of must have that opposite direction. So again, the order does matter. So in an equivalence relation, we have to essentially have both ways. And then we have something called transitivity. So essentially, if we have 3 elements of the set, if A is related to B and B is related to C, then A is also related to C. Come on, there we go. So essentially we'll have these relations. If it follows those 3 properties, then it will also be considered an equivalence relation. So every equivalence relation is a general relation, but not every relation is an equivalence relation, like squares and rectangles. Let's look at a couple examples of this. I'll try to leave those rules in. So this next one makes a bit more sense if we were actually sitting in a room, but let P be the set of people in our classroom, if you will. Pretend this is a Thursday and there's actually people here. So for any X or Y in your set P, so for any 2 people in the room, shall I say, maybe I should avoid using the word 2 people. Anyway, so let X be related to Y if X sits directly next to Y. So if one person directly sits next to another person. Explain why R, that relation, is not reflexive. So again, reflexive means that something would have to be related to itself. So here we would want essentially we want X to be related to X. Well, what would that mean? That would mean that X sits next to X, sits next to X. A person can't sit next to themselves, which essentially is the reason this isn't going to be reflexive. So a person cannot sit next to themselves. So this relation would not be reflexive, and therefore not an equivalence relation, because we would have to follow all three, and if it's not reflexive, then we're already good, we're already done. I do want to take this a tiny step further, I think, though, and just touch upon the other two pieces. Oh, why do you keep zooming in randomly? For symmetric or symmetry, we'd be good here, because essentially if someone sits next to someone else, then, you know, the other person's still sitting next to that first person, you know? So if, you know, person one sits here and person two sits here, well, then person two is still sitting next to person one. So this would be symmetric. But if you think about transitive, again, we weren't really asked these, I'm just kind of doing an extra side note here. So transitive, you know, if you have X sitting next to Y, so if X is related to Y, and then Y is related to Z, well then Y is sitting next to Z. We actually wouldn't have that X is related to Z, specifically because we were told that they sit directly next to them. So essentially, if you think about this transitive relationship, if X sits next to Y and Y sits next to Z, X does kind of sit in the same row, if you will, as Z, but they don't sit directly next to Z. So this also wouldn't be transitive. Again, we weren't asked that part. That looks like a regular old X instead of a crossed out. But just in case we wanted to take that a little bit of a step further, it would be symmetric, but it wouldn't be transitive. But anyway. Now this is an example of a case where we actually know what the relationship between these two elements are. We know that it means that someone sits next to someone else. Again, we don't necessarily always know that. So in this next example, we're just kind of told that these things are related to each other, and we're not told why. We're not told, you know, if there's kind of some actual relationship between them. We're just essentially given, hey, these are related to each other. So let's look at this one. So let me scroll down. I did record this, right? Yeah, okay. So are the following equivalence relations on the sets 2, 5, and 6? Why or why not? Well, they're all going to be relations because they're all just using the elements 2, 5, and 6 in these kind of coordinate pairs, if you will. So let's start looking at this. We want to say, is it reflexive? Well, that would mean for essentially, if we have an element in the set, in the relation, it needs to be related to itself. So note that in this relation, we've got 5s going on, we've got 6s going on, and we've got 2s going on. So we essentially use all of the elements of the original set. So what we would need is we would need essentially 2 related to 2, which we have. Catch up to me, screen. You can do it. I don't know if yours are lagging as much as mine, but just in case they are, I will wait. There we go. So we would need 2 related to 2, which we have. Excuse me. We would need 5 related to 5, which we do. And we would need 6 related to 6, which we do. Maybe, you know what, I'm even going to write it like this instead. 2 related to 2, which we have, and 5 related to 5, which we have, and 6 related to 6, which we have. So this definitely is reflexive, so we're good on that piece. About symmetry. Now, for symmetry, it's just if you have the one, then you need the other. So like, you could say that 6 could be related to 2 in general, but that's not part of our relation, so we don't need to worry about it. But we have that 2 is related to 5, so we need that 5 is related to 2. Since we have one of them, we need the other. And it wouldn't matter if you had said we have 5 is related to 2, and therefore we need 2 is related to 5. Like that, either way you do it is fine. But we have, that 2 is related to 5, so we would need essentially the opposite direction, if you will, which we have. So we have that 2 is related to 5, and 5 is related to 2. So this would be symmetric. Hopefully that makes sense. And then what about transitive? Well, for here, we would need some A is related to B, and we'd need some B is related to C. We would need that setup in this relation to be able to look at whether or not it's transitive. This actually doesn't happen. Well, you could be sassy and say that we have 2 is related to 5 and 5 is related to 2, and then 2 needs to be related to 2, but that is taken care of already. So I guess technically you could be sassy and say that, you know what, let's keep that. No, we don't need to. Because essentially all situations like this, no, wait, because that's, nope, I'm getting ahead of myself. Not ahead of myself. That actually doesn't fall out to this pattern because we don't necessarily say that A is equal to C. So never mind. For transitive, what you're specifically looking for, so sorry, I went on a little bit of a tangent there. For transitive, what you're looking for is you're looking for A, B, and C to be completely different things. If they're not different, say if A is equal to C, like I just wrote down, that's all taken care of in essentially these first 2 steps. If it's symmetric and it's reflexive, then that kind of special situation is already taken care of. The transitive piece, the thing we actually need to care about is when all those 3 elements are actually different. But we don't have that situation happening here. So we have no cases of A is related to B and B is related to C. Which kind of means that we're just vacuously true to be transitive. Because there's no cases to check, so we're actually fine. So this would be an equivalence relation. I will say, if you had written down, 2 is related to 5 and 5 is related to 2, so we need 2 is related to 2, the thing that I wrote down and then erased. If you wrote that down, you wouldn't be wrong. It's just kind of unnecessary to check because of the fact that A equals C in that case, which again is technically taken care of in the reflexive and symmetric cases. But if you had written that down, you wouldn't technically be wrong. We just didn't necessarily need to consider it because it wasn't technically a transitive case. Hopefully that makes sense. Questions and concerns on that one before we do the next one? Okay. Change color back. What about this next one? So we have a completely different relation, still on the same set of 2, 5, and 6. Is it an equivalence relation? So first thing we want to look for is reflexive. So are any of the elements that show up here, so we do include 2s, 5s, and 6s, so we would have to check all of them. So is 2 related to 2? Yep. Is 5 related to 5? Yep. Is 6 related to 6? Yep. Because of these right here. Hopefully that was clear before. Sorry. So since we have 2, 2, 5, 5, and 6, 6, those things are related to themselves. So we are reflexive. Well, what about symmetric? Well, now we're looking for essentially some A is related to B, where they're not the same thing, because again, if they are the same thing, it's essentially taken care of in the symmetric case. Well, we have 2 is related to 5. So I need to know, do I have, this notation is not like proper notation, but it gets the point across, so it's fine. So whoa, that's not one. Let me use the same notation. So we have 2 is related to 5. So for this to be symmetric, we would need 5 is related to 2. Well, we have that. We have 5, 2 as well. So we're okay in that case. Well, is there any other cases? Well, we have that 5 is related to 6. Well, do we have that 6 is related to 5? Yes, we do. It's directly next to it. Doesn't have to be directly next to it, just has to be somewhere in that set, but it shows up, so we're good. So we're reflexive, we are symmetric. Well, what about transitive? Well, we need some A is related to B and B is related to some C, where these are all different because, again, if they're not different, they're technically already taken care of in the symmetric and the reflexive cases. Well, in this relation, we have that 2 is related to 5 and 5 is related to 6. 2 is related to 5, 5 is related to 6. If my pen will work. 2 is related to 5, and 5 is related to 6. Which does kind of match the pattern that we want to look at for transitivity. So essentially, if this is going to be transitive, we would want to have that 2 is related to 6. Do we have that 2 is related to 6 in this relation? No, we don't. So this is not transitive. So this is not an equivalence relation. And once again, here we don't know what the actual relationship is here. We're not told what it is. We don't need to know as long as we're given the entire relation set. And we're just looking to see kind of whether they're paired with the correct numbers. Now, again, both of these are relations, but only one of them turned out to be an equivalence relation. So to show that a relation is an equivalence relation, all 3 of these things must be true. Does that make sense? Questions, concerns about equivalence relations? I'll leave this up for like 5 more seconds in case people need to catch up a little bit. As always, please tell me if I'm going too fast. Just sitting here in my office with 3 screens is very weird. I don't like it. All right, so let's do another one where we're kind of, it's less of just being given a set, and now we're going to actually have the relationship. It's everyone's favorite thing, seeing as how almost no one answered the divides question on the exam. So we're going to talk about divides. So say we have 2 integers, a and b, and we're going to define a relation on that set of integers. So a is going to be related to b if this is true. 3 divides a minus b. So let me remind us what that means. That means that a minus b equals 3 times something for some integer. We're going to show that this is an equivalence relation. And what this is actually going to do is it's going to essentially be an equivalence relation for something called modular. And it's essentially going to be that 2 things are related to each other mod 3. We're going to talk about this notation a bit more in a second. But that's kind of what this relation is actually doing. It's building this idea of this modular idea that we haven't talked about yet. So if you're like, what the heck is modular? We haven't gotten there yet, but we will. This is kind of like a sneak preview of it, if you will. So let's say we want to show that A is related to itself. So we want to show that it's reflexive. So essentially we want to show, if you let me abbreviate, we want to show that 3 divides a minus a. Let me put that in parentheses to be better at that. Well, if you think about a minus a, that's just going to mean that we want to show that 3 divides 0. So since a minus a equals 0 is an integer, because remember with these things, even odd divides, those were the 3. The fact that these things end up being integers is highly important. So we're just going to say 0 is an integer. Then essentially we can say that 0 equals 3 times 0, because we essentially want to say that 0 equals 3 times something. Well, can we find that something that makes that true? Yeah, just let that k value be 0. And since 0 is an integer, we're good to go. So since we can write it like that, then 3 does divide 0, and therefore a is related to a. Well, now we kind of want to show that it's, so this was essentially showing it's reflexive. And we want to look at symmetry. Is it symmetric? And then we're going to do transitive in a second. So if I want to show that this is symmetric, I need to show that if A is related to B, then it's also the case that B is related to A, and essentially in both directions, if you will. If we're just showing it for a general set where we're just given the relation, we can kind of just show the two pairs next to each other. Since this is, since we don't have the actual set written out here, we kind of actually have to go both ways. So in the one we were just doing before this, if it'll scroll up, I was kind of just going in one direction. But when you're given the set like that, it's kind of obvious that if you go the one way, you must have the other way as well, because those two things are just right there in front of you. Since we don't actually have the given set here, like we don't just have a list of things, we kind of have to show both ways. So we're going to have to show that if A is related to B, then B is related to A. And we're also going to have to show that if B is related to A, then A is related to B. Now the nice thing is that pretty much most of the time these come out to being essentially the same exact proof, so we'll eventually get to a point where we can just say the proof is similar. And we're going to do that now, but anyway. So if A is related to B, that means that 3 divides A minus B. So what that's going to give us is that A minus B equals some 3 times K. Well, if I think about what I want, let me put that over here. I want that B minus A equals 3 times, let me say J, just to say that it doesn't have to be the same thing. So we want, B minus A. Well, thinking back to our ideas of proofs, here's what we have to work with. Can we somehow get to something that looks like that? Well, how's a way that I could get B minus A out of this? Well, essentially, if I could flip that around, that'd be great. Now, I can't just flip-flop the letters because that's subtraction, and that's not how that works. But let me say I multiply everything. And when I say everything, I mean you have to do it on both sides. Never just do one thing. Nope. Words. Never just multiply one side by a number. If you multiply one side by a number, you have to multiply the other side by a number. So let me multiply both sides by a -1. So we'd essentially have negative A plus B equals negative 3K. And now I could essentially rewrite this as B minus A. Now I can flip-flop it around because it's addition. Maybe to be super clear of why I can flip-flop that way and I couldn't flip-flop the other way. I can technically flip-flop this, but it would turn out to be negative B plus A. So I could flip-flop it, but the negative would have to stick with the B. Whereas here, that's kind of what's happening here, is I flip-flop them around, but the negative sticks with the A. But anyway, just in case that wasn't clear in the algebra. And then I should technically write as 3 times negative K, because I want it to be 3 times something. Well, negative K is an integer, which I'll write like this because I'm starting to run out of space. So we have shown that 3 divides B minus A as well. The other way, proof is similar. Now, when the heck can you use that phrase? A lot of times you'll be able to do it when we're proving the symmetric idea. But essentially, if you think about proving it this direction, we would have started with b minus a equals 3k, and we would have ended up with a minus b equals 3 times negative k. So essentially, it's the exact same thing, but the letters are just in the opposite order. Since it's the exact same thing up to kind of the ordering of the letters, if you will, we can kind of just say the proof's similar. Just follow the work you just did, just with the letters in the wrong spot. Not the wrong spot, I should say a different spot. So it's not that we're really, it's just that you don't have to necessarily write out the exact same work you just did if it's the exact same steps, just with different letters. Anyway, so that shows that it's symmetric. If I have one thing related to something else, then we kind of have that opposite order as well. Questions, concerns on that before I go to transitivity? Okay. So this is transitive. Let me kind of come off to the side for this one really quick. So we have that A is related to B and B is related to C. So we have A is related to B. So 3 divides A minus B. So A minus B equals 3 times something. We have B is related to C. So 3 divides B minus C. So B minus C is equal to some 3 times, well, let's do K sub 1 and K sub 2. K sub 1, K sub 2. What we want is for A to be related to C. So I'm running out of space. A minus C. Let me just jump to the kind of end point here. We want A minus C to be equal to some 3 times something. Well, how can we do that? Well, let me start with A minus C. This is a typical trick that is used a lot, not even necessarily just in these transitive proofs, but just in general. If I rewrite it like this, whoops. What I've essentially done is I've added in kind of this piece right here. But that's essentially adding in something and subtracting it out at the same time. Notice we have plus B and we have minus B. And if you think about it, negative B plus B is equal to 0. I can always add in 0 if I want to. Adding 0 to something doesn't change it. So I can essentially add in those kind of two pieces there. And what that allows me to do is I essentially now have A minus B and I have B minus C, which is essentially what I have to work with what I was given. So now I can essentially replace that A minus B and that B minus C with their kind of 3 times something pieces from the fact that we had the divides relationship. Come on, screen. There we go. And when I make that replacement, well, I'm looking for 3 times something, so I could factor 3 out of here. Why do my 2's? I just go back and forth on how I write my 2's. Come on, screen. There we go. So if I factor 3 out, I essentially have that setup of 3 times something. And we would want to say k sub 1 plus k sub 2 is an integer by that axiom 1 from a while ago. So 3 divides A minus C. So A is related to C.
Can you explain axiom 1 again? It confuses me.
Explain what?
Axiom 1 again.
Yeah. So if I scroll down a little bit, where's some space? So axiom 1 was from section 1.5, possibly 1.4, but I think it was actually 1.5. essentially says, oh God, what did it say? I don't remember the formal statement, but it was something like if A and B are integers, then A plus B and A times B are integers. So essentially the point of this guy is we kind of take it for granted that when we add two numbers together, we get an integer, and when we multiply when we add two integers together, we get an integer, and when we multiply two integers together, we get an integer. But it's something we kind of have to, again, take for granted, so it's technically considered an axiom. So what this axiom allows us to do is essentially allows us to say anytime we have two or even more integers, if we add them together or if we multiply them together, their result is still an integer. And I can also, add them, and, if we add in some more integers, I could have like a string of integers multiplied and added together, and the result would still be an integer. That's essentially what this axiom is telling me. So the point of it is that with these definitions, even, odd, and divides, there's a big piece of them that always says that kind of that number that you have has to be an integer. So like with this divides case, we have that it's equal to 3 times something. Well, that something has to be an integer or else it doesn't actually hold. Like for the definition of divides to work, that number that you multiply that 3 by has to be an integer. So essentially when we're doing kind of this proof that we were just looking at, we get out to something 3 times k sub 1 plus k sub 2. So we have to show them that that k sub 1 plus k sub 2 is actually an integer, because if it's not, then we haven't satisfied the definition of divides. But we kind of have this axiom that comes and saves the day all the time that just says as long as you're just adding or multiplying integers together, you still get an integer. Does that make sense?
Yeah, thank you.
Hooray. So it's just essentially the thing that helps save the day and always tell us that what we want to be an integer actually is an integer. But we kind of have to say that it's by that axiom, we kind of just can't take it for granted. All right. Any more questions about that example? Or anything related to that example? Okay, we can probably get through 204. Okay, we're going quicker than I expected, which is good, I guess. Definition. A partition of a set S is another set, P, of non-empty subsets of S with the following properties. And I'm going to draw a picture that I think will make everything make a bit more sense. So it has the following properties. For any element A in the set S, there's going to be some. Now, this is a set because P is a set of sets. So essentially for every element, there is a set that that element is in. And again, hopefully the picture I'll draw in a minute will make this make more sense. So the elements of P are going to be called the blocks of a partition. So actually, let me draw the picture right now so I can keep referring back to it. So say we have our set S, represented by this circle. Essentially what a partition does is it kind of breaks this set up. You know what? No, nope. I want to draw this one first. Boink, boink. And these are just randomly chosen. So essentially, if I break this set up kind of into, these littler sets, if you will, essentially the partition is going to be kind of the sets. It's going to be a set of these sets. It's kind of going to be the set of the things that I broke it up into. So these things are called the blocks. And essentially what this kind of first idea is telling us is that every element of S, because remember this started out with actually being this set S. So every element of S belongs to a block. Every element in S must be in kind of one of those kind of mini sets, if you will. And then if we have two different blocks, X and Y, if they're different blocks, they're not the same block, then their intersection must be empty. So essentially these blocks, maybe I'll say the blocks, don't share elements. Oh, my camera froze. Not that the camera really matters, I think, because it's so tiny, but anyway. So essentially, think of taking a set and just kind of breaking it up into pieces. So, and it's not even necessarily that they have to be, how do I want to phrase this? It's not even necessarily that you have to be particular about which things go where. It's just imagine, you know, taking some set 4, 5, 6, 7, 8. If it'll catch up to me. Whoa, hello. There we go. So kind of, woo. It always freaks me out when it zooms in. So side note, say I had some set 1, 2, 3, 4, 5, 6, 7, 8. I could break this up into essentially the even numbers. 1 is not an even number. 2, 4, 6, 8. And then all the odd ones. So 1, 3, 5, and 7. Whoop. There we go. So essentially, breaking it up into even versus odd would be a partition. So essentially, the two sets, say I name the even one E and the odd one O. So my partition would be made up of those two sets, E and O, once my screen catches up to me. There we go. Maybe I shouldn't use O because it looks like a 0. I'm going to erase this in a second anyway. Now, also, the point I was trying to say before is that these blocks, these kind of ways that you're breaking it up, also don't need to have like a relationship. Like I didn't have to make it even and odd. I could have taken 1 through 4 in one piece and then 5 through 8 in the other one. That would have been a completely different partition. The only thing that needs to happen is essentially every element goes into some block and the blocks don't share elements. We're essentially just taking a set and breaking it up into a bunch of pieces. So that's the idea of a partition. So I'm gonna, no, I'll leave in a side note. Although I want to change this O because I don't like it looking like a 0. I'm gonna name that D because that's the next letter in odd. So I'll kind of leave that side note there. Now, the next thing is a theorem. And of course, theorems in math are always look terrifying. But I tried to tell you what it says kind of in plain English down here. But essentially, we have this theorem. So if we have an equivalence relation R on a set S, then for any element S, we can essentially define this new set to essentially be all of the elements related to X. So we have a relation, and what we're going to essentially do is we're going to break up the set into kind of all of the pieces that are related to something else. So if we let P be the collection of these subsets, then that P is essentially going to create a partition. So essentially what this theorem is saying is this theorem says that every equivalence relation, not every relation in general, every equivalence relation forms a partition. And every partition also forms a equivalence relation. So essentially it goes both ways. If you have a partition, you can have an equivalence relation from it. Or if you have an equivalence relation, you can get a partition. If you really want to see a proof, it's in your book. So essentially, partitions and equivalence relations are going to be the same thing. So essentially, what equivalence relations are going to do is they're going to break up a set into a bunch of different pieces. So the sets R sub X in that scary theorem, these are called equivalence classes. Now you could also think of them in terms of as blocks, but when we talk about an equivalence relation, we use the phrase equivalence class. But that's kind of the same idea, is that these equivalent classes are essentially the blocks of our partition. Now, if I could, woo. Stop it. If I kind of draw that same picture that I just had. Boink, 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 boink. But let me rename them kind of in terms of this R sub whatever language. So we have kind of this kind of partition of this set. And notice that I've named them R sub something instead of just, you know, X sub 1 or X. So this A, B, C, D, and E would be considered elements of S once my screen catches up to me. So essentially we're going to name these equivalence classes in terms of an element from the set. And these are going to be called the representatives of their equivalence classes. That's an S. Mm. 15. Yeah, I guess we'll just keep going. So we might not get to the full example today, but essentially what we're going to see is essentially what happens is we have this set, we're going to break it up into these kind of subsets, into these pieces, and we're going to essentially refer to each piece in terms of one of the elements of the set. And everything in that piece is going to be related to that element. And again, I don't think we'll get to the full example of it today, but I'll try to point that out again when we get there. So the way we're going to look at this and the main equivalence relation we're going to consider in terms of this partition idea is something called modular. We're going to talk about modular arithmetic as well, but we kind of have these sets that have this mod relation that we'll learn, and we'll look at that in terms of being an equivalence relation. But before we can talk about that set, we kind of need to talk about what modding and modular arithmetic actually is. So we need to build up this idea of modular arithmetic before we can actually talk about that equivalence relation. So we'll talk about that first, which is why I don't think we'll get to that example today. But anyway, so theorem, which is called the quotient remainder theorem. This is kind of something that you pretty much already kind of know in your brain. You just might not think about it in terms of this much generality. So let A and B be integers such that B is greater than 0. Ooh, that's not written very nicely because that and in the middle. Let me try to rewrite this so that it looks better. LaTeX did not space that out as much as I would have liked. Yeah, that's better. So say you have two integers, B has to be positive. There exists integers Q and R such that you can write A equals QB plus R, where R is going to be between 0 and B. Now, essentially, the reason you kind of already know this, but you might not think about it in this much generality, is this is essentially dividing. you can always divide a number by something else and get a remainder. The remainder might be 0, but you can always divide a number by something else, get a quotient and a remainder. So we essentially have this pair of integers q and r that satisfies these conditions, where q is going to be called the quotient.
I have a comment.
Yeah.
We use mod all the time in coding as a way to determine whether a number is even or odd.
Oh, cool.
So if it comes back with, that it's equal to 0, then it's even number, and if it's not equal to 0, it's odd.
Oh, I did not know that. That's cool. So y'all might already know mod. Never mind then. But anyway, we're going to talk about it in more generality than just zeros and ones, because I know y'all probably work in binary a lot. But anyway, that's cool. I didn't know that. So we've got q is the quotient and r is the remainder. So yeah, kind of like I think it was Ryan was saying, in terms of just even and odd, if you divide an even number, if you get a remainder of 0, then you know it's even. If you get a remainder of 1, then you know it must have been odd. Essentially because, you either get 2k or 2k plus 1. Did you get a remainder of 0 or a remainder of 1? That's cool. Anyway, my screen's now frozen and I want to move on, but I want it to pop up really quick. There you go. Or not. No, I'm just going to erase it. Okay. I was just babbling anyway. So say we look at these. So we have an A and a B, and we want to find essentially our quotient and our remainder. So thinking, like way back to elementary school when you're doing division for like the first time ever. So we have A is 37, negative 37. So we're going to want negative 37 to be equal to something. And so if we think about kind of what we have to multiply 5 by something and then add on a potential remainder. So what is kind of the largest number we can multiply 5 by that's less than negative 37? And the answer would be negative 8, because that would get us negative 40, which is less than negative 37. And then we'd have to add on an extra 3 to kind of bring it back up to negative 37. So the one thing is you need to be careful, because here essentially our q ended up being negative 8 and our r ended up being 3. This number must be between 0 and 5, which is why we're kind of forced to let our q value be negative 8. So you might say, well, what if I let it be negative 7 and then I just subtract 2? Well, that wouldn't work, because your remainder always has to be between 0 and your b value. So that's why we're forced to essentially take it down to negative 8. So our remainder would be 3 and our quotient would be negative 8. What if we change that negative to a positive? So now we want it to be 37 equals something times 5 plus something. What is kind of the largest integer that you can multiply by 5 to be less than 37? In this case, it would be positive 7 to get us to 35, and then we could add 2. So our quotient is 7 and our remainder is 2. So notice, if we solve the above equation, and by the above equation it means this one. That one. If we solve that for r, you would get r equals a minus q times b, which you can kind of see that we're essentially subtracting multiples of b, and then the remainder is the smallest natural number that we can form in that kind of fashion. That's just, I don't know, a little tidbit. Not really that important to remember, but. So I think the last thing is we'll just take a definition of modular, which some of you may have seen before in your life. Maybe some of you haven't seen mod yet. Maybe you haven't gotten to the classes where you use mod, but I definitely believe coding. You are right, Ryan. Coding does kind of use mod. I'm not a coder. I should have asked my dad. He's a professional coder. He does weird things. Anyway, so in example 7, we defined an equivalence relation. We were doing that divides thing. So we could do this for absolutely any integer, not just 3. You could essentially do the same proof, just instead of wherever you wrote a 3, you would write an n. So essentially we have this idea where if you have any two integers, and for some integer we have that n divides a minus b, what we're going to have is we're going to say, and I'm going to write it in quotes, is a is equivalent to b modulo n. And you would write it as a is equivalent to b. Now, I always write my mod n in parentheses. Sometimes you can drop the parentheses. I think it's more of a math thing to write it in parentheses, so I will probably always write them, but you can definitely write it without the parentheses, and it's fine, like it does right here. So essentially we have that a is equivalent to b mod n if and only if n divides a minus b, which if you remember, if we use the definition of divides, then a minus b must be equal to some n times k for some integer k. And then we can kind of add that b over to the other side. And this is kind of bringing it back to that quotient remainder type idea. It's in that kind of similar format, which is not a coincidence. So essentially, we're going to be, and again, I don't think we'll get to finish this today. I think we're going to stop here. But essentially, we're going to look at now this equivalent class formed by this equivalence relation that's called the integers modulo n. In general notation, we will write that set as kind of that integer symbol divided by n. So what we're going to do on Thursday, because we don't have time to jump into it now, is we're going to kind of look at this specific equivalence relation of these integers mod n. We're going to do a little bit of modular arithmetic with it, which again, I think is pretty fun, but y'all might hate, I don't know. But we will talk about that on Thursday, and we will wrap up for today a tiny bit early. So stick around if you have any questions. Otherwise, feel free to leave. We'll finish up 2-4. And oh, let me quiz. What do I want your quiz to be on? What do I want your quiz to be on? That's a good question. Well, it would have to be on 2-4 because that's all we've talked about so far. Okay, so it'll definitely be on determining whether or not something's an equivalence relation. So let me start typing this in chat too. So quiz on Thursday will be on 2.4 because we haven't covered anything else yet. Determine whether something is an equivalence relation. It will be more like example 6. And maybe even a tiny bit like example 5, where it's kind of a contextual, maybe not even contextual, but where you're kind of given the relation between the two. I don't want to say it'll be like example 7, that's a bit too far, but I also don't want you to think that I will necessarily give you the entire set. Maybe I'll tell you what the relation is and ask you, is it an equivalence relation? But it would be more like something like example 5 than example 7, where we kind of had to do it in the full generality with the divides. So that kind of idea of determining whether something is an equivalence relation or not will be essentially the basis for your quiz on Thursday. Okay, now we're done. If you have questions, feel free to stick around. Otherwise, have a good day. I'll see you on Thursday. Yeah.
Could you, when will you be uploading this?
Uploading what, the recording?
The notes, the
notes?
Just, yeah.
I can do that literally right now because I have another class right after this, but I'll just plop it up there. Right.
I have a tutor that likes me to send it over to her so she can review it before we meet.
Got it. Yeah, I mean, I usually try to put it up after I get done my classes, but if you always just want to hit me with a quick reminder at the end of class each time, hey, can you just put those up right now? I totally can. It takes about like 2 seconds. I just usually don't think about it until after I'm done teaching. There we go.
Thank you.
Mhm.
Another thing we use the mod for in coding is, well, say like we'll make a converter between decimal and binary,
Mm-hmm.
and they will, so like you'll use the divide and you'll take the whole number and it will truncate the remainder off of it. And so you use that to determine what the place is, and then you use the mod to determine what your next place is, like, and you calculate it out of that.
Yeah.
And you just keep, and then you keep going like that until you get through all of your
That makes sense.
places.
Yeah, that's cool. Binary's pretty weird. I once spit a number out to my dad and he told me what it was in binary in about 5 seconds, and I was like, you're an alien. That's cool. I didn't think about using it like that, but it makes complete sense. Cool.
But yeah, I imagine certain numbers are really easy. Like 15 is just 1111. So I mean,
Yeah.
something like that would probably just stick in your head.
Yeah.
But we don't deal with ones and zeros as much as you would imagine. At
Right.
least not at the level we're doing now. So.
Right.
Right. Thank you.
I feel like hexadecimal would come up more often.
That comes up a lot with networking. The IPv6 network addressing is all in hexadecimal.
Ugh, sounds gross.